Okay, Kirchhoff's second rule, that is also called the loop rule, is just a consequence of the conservation of energy. That means if you have, for example, a circuit, like a closed loop circuit, right? Well, like one single loop circuit with two components, that means that the sum of the differential potentials in these two components, they should be equal to the energy, to the differential potential that is supplied, that is powering this circuit. Kirchhoff's second rule stated that the algebraic sum of changes in potential around any closed circuit path or loop, that's what they call like the loop rule, must be zero. That means, in other words, that the energy is conserved in a loop, what is expected, right, guys? So let me actually solve one example, and then this is going to become clearer. Let's see, for example, for these kinds of circuits, right? Let's imagine this circuit here. I'm going to show my whole share screen with you guys, and I build this circuit here too in a simulator, right? If you close this, okay, you have I'm supplying here, as you can see. Look guys, I'm supplying to this circuit with 12 volts, right? And you have one resistance of 1 ohm, 2 ohms, and 3 ohms. And if we measure the difference in potential here, let's see, you have, see, 2 volts here, you have 4 volts here, and we have 6 volts here. And the total, as you can see, you have 6, 4, and then 2. If you sum the difference in potential of these three resistors here, they are exactly the same like the difference potential that is actually powering the EMF here, the electromotive force that actually powering this system. This is the second rule, Kirchhoff's second rule, and that is very easy, guys. It's saying that every closed loop here, you have this summation of these potentials are zero. We can actually write for this one, you can start in point A and going clockwise to point A again, should be closed loop, remember this. So we have here, for example, V, that is the electromotive force, minus this V1, we have a decrease in potential there, then we have a decrease in potential in the second resistor, and then we have also a decrease in potential here, and this should be 0. We can actually see that this is going to be 12 minus, we can use Ohm's second law here to solve this problem. This is going to be I1, this R sub 1, minus I2 sub 2 R2, minus I sub 3 R3 equals 0. Guys, let me call you again. Give me 1 second because it's going to fall in. since this is a series circuit, right? So that means that we have the same current like flowing through every single component here in this loop. So I can actually, I don't need to keep the indexes here. I can actually lose the indexes because they're all the same current. So I can just use I, and R1 is 1, so I have I, R2 is 2, I have 2I, and R3 is 3I. This is equals 0. Let's organize this a little bit. I can solve this. This I have minus 6I, so 12 equals minus 6I equals 0. That means that this current here is going to be 2 amperes. Okay, let's just highlight this result here, guys. And this is Kirchhoff's method, right, that we use to solve this circuit. But also remember, it's very, I'm going to put this here as method 1. So we have this unknown, we didn't know the current here, right? We have no idea about the current like flowing through this circuit using like the Kirchhoff's law, second law here, loop rule. We found, so this was the, let's make this a little bit more organized because I wanna also just to take a trip to memory lane and go back to high school. And we are going to solve the exactly the same like the way we did in high school. In high school is actually we try to concentrate in simplifying the circuit and then solving it to find the unknowns. In this case here, all you have to do is actually, since we have like 3 resistors in series, we just have to sum these resistors here. So the first thing that we do is actually calculate the equivalent resistance for a series case. So this means I'm going to sum up R sub 1 plus R sub 2 plus R sub 3, and this is going to be 1 plus 2 plus 3 in our example here. So this equivalent resistance is 6 ohms. And then here you just have to apply Ohm's law again. So we have the electromotive force there is going to be equals to the equivalent resistance times the current like flowing through this circuit here. This one I have is 12 volts. The equivalent resistance is 6. I just calculated I. That means that I here is equals to 2 amperes. Exactly the same result that we found like using Kirchhoff's second rule. Why you have this one? As I cannot stress this enough. We have these different techniques now to solve the circuits, because not every single circuit is going to be as simple as this one that you can see now. Remember, if you just go back like a couple of slides ago, for example, here you can see this, for example, this circuit here. This circuit is not so easy, and it has many components, right? Some with different natures, so it's not going to be so easy to solve for this circuit. So that's why you need like another type of techniques, and you need different techniques to solve. Just to finish this part here, so this is one example for a single loop circuit of how to use the loop rule, right, to solve that. Just to finish this, I would like to show you again the simulation here. Whoa, let's close here. Let's go to our simulation here, and again we can see, let's see the current here. As you can see, guys, again we can actually see that the current here is 2 amperes as expected, as we calculated using like the equivalent circuit like technique and Kirchhoff's law. Oh, beauty, my god, this is so beautiful. Physics, mathematics. Okay, guys, I would like to make some very important comments and on how to do. So we need some kind of conventions, right? When we need some kind of a strategy to apply Kirchhoff's laws to any kind of problem, and this is very important. You have to be consistent if you want to solve a problem, especially when you have a very complicated circuit. It's very important to be consistent. In this case, the strategy is very easy. The first thing that you do, you have to label points in the circuit diagram using lowercase letters, A, B, C, and so forth. The same way like I did for this one is already done, but this one is actually not so important. When you have like multi-loop circuits, is going to be crucial to solve the problem. It's also important to locate the junctions in the circuit, and not only that, once you locate the junctions, so I'm going to make one small comment going back, for example, to this example here. Let's go back just for a couple minutes here before you keep going, because look, for this you have 2 loops, and you have, let's pay attention here in this junction B and in this junction D here for this circuit. If you write, actually let's copy this to a different location here, so you can actually see this without all this visual pollution here. Let's copy this to a different, because this is very important. Very important point here in this junction B, when you are solving for a little bit more complex like circuits. So if you write, let's now we wrote like the equation, right, for the junction B. If you write for the junction D, what you're going to realize, for junction D you have I1 entering, right? So this means it's positive y sub 1, I3 also plus I3, and this one is going to be leaving, so this means negative minus y2 equals 0. This is for junction D. Let me put this a little bit down. Let's move here. As you can see, these 2 equations here, guys, I can erase this. They are not linear independent, they are dependent. So when you're choosing your junctions in the circuit to solve, right, for the unknowns that you have, even when you're designing a circuit or when you're trying to calculate the load in portions of the circuit, when you're like solving problems in our, for the homework, or doesn't matter if you are kind of bored to death and you just wanna solve some electric circuits to be happy, it's very important to pay attention on that. Okay, so please do not choose junctions that actually are dependent, because the equations that you are going to find, they are equivalent, right? They are the same, they are linear dependent, and then you cannot solve. Remember, if you have equations that are linear dependent, that means in your matrix you're going to have at least two rows, right, that are going to be dependent, and then you cannot solve, right? The determinant is going to be 0, so it's not going to work in this sense. Okay, let's go back to what you are saying. Let's go back to our rules, right? Our strategy to solve. This is very important. Okay, so make sure that at least one current point in the junction, at least one current point out of the junction. Very important. Okay, then after that, right, labeling, locating some junctions that do not give you linear dependent equations, you have to choose a couple of loops in the circuit. And this is very important, guys. You have to be deadly sure that at least one component must be contained, right, in one loop. And of course, as you can see, for example, for this one, this one, sometimes you have one component that is going to be in more than one loop, right? If you consider this one loop and this one loop, this component R sub 3 here is going to be part of this this loop here, and is going to be part of this loop here. Let's go for our strategy. And then, guys, you just apply the junction rule. You write, those equations, being consistent, and you apply the loop rule, and that's it. And then you'll be happy. Just you have to remember two things, guys. Okay, if you have, for example, your component is a resistor and the current is this way, is going from A to B, and you are going the loop in this direction, right, when you are traveling the loop, so that means a negative difference in potential. If you are going this way in your loop, that means positive. Very important to keep this. This is going to be a positive, negative. This one is going to be a positive. And as you go through, when you're traveling in your loop, when you go through the sources, right, the EMFs, if you go this way, if you're going this way, we consider positive too, and if you go in the opposite direction, we consider this negative. This is going to be clear now as I solve one problem for you guys. I'm going to go through a problem very slowly, just presenting you the rules. You just have to apply these rules. So with this being said, I would like to move to the next part.